faster, and it goes farther. Fire it fast enough, and it goes into orbit. It becomes a satellite, like the moon around the Earth. Newton's genius was to recognize that the force that makes a cannonball fall to Earth is the same force that governs the motions of moons and planets. It's the force that dictates the speed of orbits. In the solar system, the closer a planet is to the sun, the faster it must move to resist the sun's gravitational pull and stay in orbit. And it's the same force that boosts spacecraft as they explore the planets. By the end of the 1600s, astronomers had a map of the solar system, but it was a map without a scale. That began to change with the study of Venus. The dot is Venus in transit, crossing the face of the sun from our perspective. Seen from two different places on Earth, Venus makes two different tracks across the sun. Using trigonometry, astronomers could judge Venus's distance from us. Similar calculations using the other planets helped provide a scale for our solar system. Measuring the distances of stars would be trickier, though. As our planet circles the nearer stars to move from side to side as our perspective of the cosmos nearby objects appear to move when viewed first with one eye and then with the other eye. In 1676, a Dane named Olaus Romer was observing the eclipses of Jupiter's moons. They came sooner than expected, he discovered, when the Earth and Jupiter were on the same side of the sun in their orbital paths. The eclipses came late when Earth and Jupiter were on opposite sides and farthest apart. The reason was the time taken by light to travel from Jupiter to Earth. Thus Romer showed that the speed of light was measurable, not infinite. Astronomers were well on their way to coming up with the units called light years that would allow us to measure unimaginable distances. As telescopes became larger, more and more stars sprang into view. Then, in the late 1700s, English astronomer William Herschel built a huge telescope and mapped even more of the heavens. Incredibly, he counted the stars one by one. There were thousands. A chart of how he thought they were arranged and put the sun near the center. Herschel thought this was all there was of the universe. Evidence that there was more came from Burghcastle in Ireland, where the 3rd Earl of Rosse built an even bigger telescope. It was the mid-1800s, and Rosse had discerned faint, wispy clouds. He drew them. Within some clouds were strange swirls. Rosse had glimpsed what lay beyond the Milky Way. Astronomers were finally coming to grips with just how far away stars were. New, precise observations revealed that stars do shift position as the Earth orbits the sun. It's hard to see because they're so far away. The effect is called parallax. It's measured by observing a star from one side of our solar orbit, then 6 months later from the other. How far the star appears to shift depends on its distance. The closer the star, the more it seems to shift. But scientists really got to know stars better by passing starlight through prisms. By splitting light, they could read the character of a star in the rainbow of its spectrum. The technique is still used today. Like a fingerprint, every star has a unique spectrum. Analyzed with a spectrometer, it reveals, among other things, the composition of a star. Spectra fall into groupings, categories that tabulate a star's temperature and its real brightness. Luminosity, as astronomers call it. A yellow star like our sun has a luminosity rating of 1. More luminous stars shine blue, rating 10. Or 100. Even 1,000. And if the temperature and luminosity are known, then it's also possible to calculate the distance of a star. For instance, if we know from its spectrum that the big star on the left is 100 times more luminous than the star on the right, then why do they shine with equal brilliance? The answer is that light diminishes by the square of the distance it travels. So in reality, the big star is 10 times farther away than the little star. From the depth of the cosmos are stars that beat like a heart. They are called Cepheids. Astronomers can tell their distance from the rate of their pulse, because a Cepheid's luminosity is related to how quickly it blinks. Cepheids are celestial beacons that help measure some of the most distant objects in the sky. Cepheids beat in globular clusters, collections of stars that hover outside the main part of our galaxy. Globular clusters are too remote to measure by the parallax method, but by measuring the pulse of a Cepheid within it, a cluster's distance can be worked out. The observation of Cepheids has helped map the structure of the galaxy. The sun isn't at the center, but 2/3 of the way to the edge. At last, the sun was dethroned from its place at the hub of the universe. But there was an Observers have seen it since ancient times. It's a fuzzy patch in the constellation of Andromeda. Near or far, no one could tell. Then in 1923, the American astronomer Edwin Hubble realized he was looking at Cepheids in Andromeda's outer reaches. So faint, they were far beyond the stars of our own galaxy. Hubble was looking at another galaxy, more than 2 million light years away. As Hubble peered deeper into space, he found more and more galaxies of every shape and size. Hubble unveiled an expanding universe. Galaxies traveled outward in all directions. The farther away they were, the faster they appeared to recede. The evidence was in their light. It shifted toward the red end of the spectrum, a sign of lengthening wavelengths. The wavelengths were stretching because the space between the galaxies was stretching. The galaxies were relentlessly moving apart. Edwin Hubble had stumbled upon the origins of the universe. His brilliant observations revealed an ever-expanding universe, a universe that may have had a single moment when time and space began, the Big Bang. Today, the quest to measure the universe goes on, but our instruments are crude. Powerful optical telescopes have a 30% margin of error. We need finer devices. Like the satellite Hipparchus, which launched in 1997. Clear of atmospheric distortion, it surveyed the nearest stars and measured distance as never before. And then there are radio telescopes, invisible to our eyes. The king of all telescopes is the Hubble Space Telescope, continuing the work of Edwin Hubble himself. The Hubble has studied Cepheids in a galaxy too distant for telescopes on Earth. The Hubble has returned some shocking findings. Its measurements of the most distant galaxies have told astronomers that the universe may be around 12 billion years old, almost 3 times as old as originally thought. Could the winking Cepheids be sending false signals? These Cepheid readings are probably right. It might take years to see them in context. Our picture of the Big Bang could well be way off. Indeed, when did it occur? And why does the universe expand? In years to come, our current ideas of the cosmos may be as quaint as those of ancient observers.